Okay, so hello students, this is Dr. Zhong. So first of all, I need to apologize for uploading this video late because um, so I actually this is actually the fourth time that I recorded this video. The first three times the videos all corrupted at let's say around 15 or 20 minutes, but I don't realize that until I finish the recording. So now it's like um, this is the fourth time that I'm recording it. So hopefully I can finish this time. It will be okay, and so that I can upload it upload it online for you to view. So before, as you can see that from my previous from my previous recordings, I made some notes on it. So before I jump, so today we are going to enter the last section of this of our course, in which we are going to talk about the graph data structure and the search algorithms inside this data structure. So, and we're going to go over this topic for 4 weeks. Okay, so we're going to learn in total 11 algorithms. It's a lot. And so today we're going to first learn the representation of a graph, say how to represent a graph by using a computer program. And then we're going to learn the first search algorithm in it. It's named breadth first search. So, but before that, I want to briefly talk about the emails that I received from you based on homework 7. So for homework 7, I received quite a few emails asking me, okay, whether if the what is the correct output, or say the students just send me a screenshot asking me if that kind of output is correct or not. So I'm not sure if you remember that in my previous lectures I told you that so the for all the homeworks I'm not going to give you to tell you what is the correct output, but instead if you pay attention to the lectures and if you understand the algorithms, either you can just figure it out by yourself very quickly, or you can find the correct output from the slides. So for homework 7, actually you can find the correct output in the slides. That is right over here. So the first test instance basically checks the longest common subsequence between two strings. Here, this is in your say main function, in the main function of your file. So I got LCS over two strings. The first string is right over here, ABC, BC, BD, AB, and the second string is BDC, BA. So yes, so here from this slide you can say that the longest common subsequence is BCBA. So what's the length? 4, right? So the first output that you expect to see from your print is just 4. Whereas this is the second test instance I used in the main function, and here this is the longest common subsequence. If you just do a very quick count, you can find that this length is 20 because it includes 20 characters. So again, for other future homeworks, don't ask me what is the correct answer. So if I tell it to you, it will not be fair for the other students. Instead, either work it out by yourself, or if you think that's too hard, or if it's not feasible for you to work it out by hand, then go back to the slides. It must be in the slides. Okay, so so without further ado, let's look at the graph data structure. So I'm going to clear this page. Also this page. Okay, so I'm going to clear this page as well as this one. So I'm going to clear all the pages so that we got a clean graph. So here What is a graph data structure? So basically, a graph is a set of nodes that are connected by a set of edges. So we use V to denote the set of nodes, whereas we'll use E to denote the set of edges. So in total, we have G equal to V and E. So because we have two components, the nodes and the edges. So on the this is one instance or one example of a graph. Here we have for V we got five nodes, so which are V1, V2, V3, V4, V5. So here I just put the numbers to denote the index of the nodes, and so here we got five nodes, and if we use E1, E2, E3, E4, E5, E6, E7, and then the set of edges include 7 edges. Okay, so this is the representation of the first graph. So it includes 5 nodes and 7 edges. And then so below it is another example of a graph in which we got 6 nodes. But the biggest difference between these two graphs are that in the first graph, the edges do not come with a direction, whereas in the second graph, the edges do come with a direction. Okay, so here for graph we have two subtypes. One tab is undirected, and the other one is directed graph. So by undirected, what we mean is that the edges do not come with the direction, but for directed graph, the edges come with the direction. Okay, so these are just two different types. Some of you may wonder, okay, so why do we have these two subtypes? And if you have this question, that's very good, and you should take this question, and it will be very clear in, let's say, 10 minutes or so. So first, let's look at why do we need to use this data structure. So first, let's look at the representation of the road network in the country. So here, so for example, we have a lot of cities in the country, and some cities are some cities are connected by a highway, whereas for some cities there is just no direct highway to go. So I'm just giving you one example. Suppose this is NYC, and here we have Montclair, and then here we have Philadelphia, and then here we have DC. So just suppose that the road network is like this. There is a highway between Montclair and NYC, and there is a highway between Montclair and Philadelphia, and then there is a highway between Philadelphia and DC. So, and also there is a highway between New York and Philadelphia. So just for that example, okay? And so with this graph, we can represent the road network in this area, okay? So this is one reason why people propose the graph structure, because it is good at representing the relationships between some nodes. And this is one example. And actually, modern GPS or modern navigation systems like Google Map or Waze, they all model the road network as a graph. And then so that if you say, okay, this is my south, and this is my I want to go from New York City to DC, based on this graph is going to search what is the shortest route from New York to DC. So that's why we need the graph data structure, and also why we need the search algorithms over the graph. So here is another example of the application of say graph data structures. So now everybody use like social networks, for example, Facebook, for example, Twitter and Snapchat. I'm not sure if it's a social network. I don't use it. I have never used it. For example, if we talk about Facebook, and here this is, let's say, this is person A and person B and person C. Okay, so we have 3 people, and A and B are friends, A and C are friends. Okay, so here we can use the graph to represent the relationship in a social network between different people. And then for Twitter, we can have similar thing. Okay, so for Twitter, we can have similar thing. Okay, we can have a couple of people. So, but a big difference in Twitter is that, say, for example, this is my Twitter account, and this is our current President Trump. So, uh, if I follow Trump, it's not necessary for Trump to follow me back, right? So here there is a so then the relationship is not mutual. It's not like Facebook. If you send me a friend invite request, if I accept it, you'll be my friend, and also I will be your friend. So the friend relationship is just mutual. But for Twitter, the following relationship is not mutual at all. So that's why so we have this kind of like we need to use the directed graph to represent the follow relationship in Twitter. So here, so for example, this is, let's say, you and we, you follow me and I follow you. So we got two edges between us. And but for me and the president, so there is only one edge that goes from me to him, meaning that I'm following him, but he's not following me. Okay, and this is the reason why we should have directed and undirected graph. Undirected graph fits the situation where the relationship is mutual, whereas a directed graph better fits the application where the relationship is not mutual. Okay, so the next question that I want to ask before we proceed, one question that is closely related to math that I want to ask is, okay, what is the number in your opinion? Okay, in your opinion. So in your opinion, if in a graph because V and E are a set, V is a set of nodes and E is a set of edges, and for set we have this operator. So it's just like two vertical line. This two vertical line means this is the cardinality operator. So if you learn, I think you should learn it from discrete math. So okay, this is the cardinality operator, which basically tells you, okay, how many elements are there in a set. So this is like a count over the set, or the length over a set. So you can take it in that way. So here, what I want to ask you is that what is the relationship between the number of edges in a graph and the number of nodes in a graph? So basically, I want to ask you, what is the maximum number of edges in a graph? So the answer is this. So V, the size of E should be at most the square of the size of V. So meaning that the number of edges can only be as large as the square over the number of nodes. This is the reason is that, okay, in the most complicated case, we have an edge between every pair of nodes, every pair of nodes. So the number of pairs of nodes in a graph is just V squared. So that's the reason why we have this relationship, and keep that in mind, because in the future when we want to do some inference over the complexity of a graph, so we need to use that. Okay, and so this is what I want to say, and so and after this math thing, let me ask you one more question. So for example, if we have a graph, so if we have a graph like this, how could you represent it by using a computer program, right? So this question is quite hard, because you don't, at least when I was a student, it was very difficult for me to figure it out. But actually there are two different ways to represent that structure in a computer program. So the first way is this. The first way is named adjacency list. So the idea is that for each node we create a linked list which stores its neighbors. So for example, for this node it has two neighbors, 2 and 5. So then it's just like for this node, we just create a linked list which stores two nodes, and the first node hold a value 2 and the second node holds a value 5. So this tells you that, okay, the first node is so in the graph, the first node is connected to node 2 and node 5. And then for node 2, okay, so its neighbors include 1, 3, 4, and 5, okay? So for node 2, basically we create another linked list which stores the value of 1, 5, 3, and 4. So and so the same applies for node 3, 4, and 5, okay? So basically for each node, we create a linked list that stores its neighbors, so that if after giving this computer program or giving the array of linked list, we'll be able to tell, okay, how many nodes are there in the graph, and so whether if there is an edge between a certain pair of nodes. So this is one way to represent a graph by using a computer program. But this way is not going to be easy, because you have to manually create these linked lists, and it's time consuming. So that's why people propose another data structure named adjacency matrix, which is much easier compared with the adjacency list representation. So for example, if we look at again, if we look at the graph on the left hand side, in which we have 5 nodes, then we're going to create a matrix whose size is 5 by 5. Okay, so this is the matrix that we created, so which is a 5 by 5 matrix. And look at here, okay, there is an edge from 1 to 2, okay? And also, let's put it in this way: from node 1 you can reach node 2. So that's why we set we set the corresponding cell 1 and 2. We set the cell with the coordination 1 and 2 with the value 1, denoting that there is, so from node 1 you can go to node 2. So it's like in this way. Similarly, from node 2 you can reach node 1. So that's why here we create a so we put 1 at the cell whose coordinate is 2 and 1. So denotes that there is an edge between a certain pair between this pair of nodes. Okay, similarly, let's look at it in another way. For node 1, from node 1 we can also reach node 5. So that's why we put the cell with the coordination 1 and 5 with the value 1, denoting that there is an edge between these two nodes. And this is the adjacency matrix representation. And here, let me ask you one question. Okay, if you are giving this adjacency matrix, if I ask you, okay, what are the neighbors of node 1? What are you going to do? How could you find the neighbors of node 1? So here you should just go to the first row of this matrix, and then if we just focus on this row, you should be able to find these 2 ones, okay? And whose corresponding column index are 2 and 5. This means that 2 and 5 are the neighbors of node 1. Yes, which is the same as what we say in the graph. Okay, so keep that in mind. This is the way for us to find neighbors for a certain node by using the adjacency list, by using the adjacency matrix representation of a graph. And you are going to use that in when you're doing your homework, okay? So here on the right hand side, I'm showing the adjacency matrix for directed graph where there are 6 nodes. So here we have 6 nodes, so we create a 6 by 6 matrix. And let's look at, okay, from node 1 we can go to node 2 and node 4. So the neighbors of 1 should be 2 and 4. That's why we set at the first row, we set these 2 cells with the value 1 and set the other cells with the value 0. If a cell has a value 0, it means that there is no edge between this pair of nodes. And so from node 2, let's look at which node can we go to. So the only node that we can go directly from node 2 is 5. So that's why in the second row, only this cell whose index is 5 has a value 1. All the other cells have 0 because there is no direct edge that goes from 2 to any other node in the graph. Okay, so this is the adjacency matrix representation, and this is relatively easier for you to create this matrix. You are just basically creating a two-dimensional array, and this is very easy for to do that. Okay, so so throughout our course, we are going to use this representation, the adjacency matrix representation, to make our life easier. And actually, this is the routine in industry too. So and after we learn how to represent a graph structure by using computer program, and now we are going to look at the first algorithm that is supported by this data structure. And the first algorithm that we're going to look at is say the breadth first search algorithm. So this algorithm takes two input parameters. The first one is the graph, and whereas the second one is just a node in the graph. So we call it the source node. So the output of this graph is like how many. So what is the minimum distance from this node to all the other nodes in the graph? So for example here. For now, let's just ignore the distance. So this is the road network in Germany, and we see a lot of cities like Frankfurt, Nuremberg, Munich, Stuttgart, etc., etc. So so suppose this within this graph, so you are supposed that you work for DHL or FedEx, and then you are at Frankfurt. You just pick up some mails to send out, so to different cities. So and then you want to know, okay, what is the minimum distance from Frankfurt to all the other cities? Here, let's just ignore the edge widths. So let's say, okay, there is a road that connects Frankfurt to Mannheim, and then there is a road that connects Mannheim to Karlsruhe, and then from Karlsruhe there is a road that goes to Augsburg. So this, you can take it as the road network. So with this algorithm, with the breadth first search algorithm, it is able to tell you, okay, so how many rows or how many different rows do we need to take from the south node, which is Frankfurt, to every other node or every other city. So for example, so to reach Munich, you need to, so the minimum distance from Munich to Frankfurt is 2, because so the shortest route is like here. You first from Frankfurt you go to Kassel, and then from Kassel you go to Munich, which takes 2 rows. Okay, so and also it will tell you, okay, the minimum distance from Frankfurt to Nuremberg is also 2, and this is the shortest route. So this is the output that we expect this algorithm to return, and let's look at how can we realize that. So this is the pseudocode, and so as we can see that this algorithm takes 2 input parameters, a graph G and a source node S. So what this algorithm does is that for each vertex that is inside the graph, but excluding the source node, okay, excluding the source node, we associate each node with a color that is white, and we associate each node with a distance, which is infinity, and we associate each node with a pi that is nil in the beginning. So let's first look at what does this value mean. So for each node in the graph, v dot d means what is the minimum distance from this node v to the south node, okay? And then v dot pi is going to be a little bit more complicated, but I can explain to you over here. So right in this example, okay, the parent of Munich is Kassel. So the reason is that, okay, if you want to go from Frankfurt to Munich by using the shortest route, before reaching Munich, you need to go to Kassel, okay? So that's what we mean by parent. Like, what is so in the shortest route, so what is the last node before this node you need to visit, okay? So, and then we associate each node with a color. So each node can actually have one of the following three colors. So the first color is the first possible color is white. We use white. We associate a node with white color to denote that this node has not been visited before. And then if this node has been visited, but and of course this node may have some neighbors. Okay, I'm just going to use. I don't have a gray. Oh, so here I have a gray color. So gray color means that this, if a node has a gray color, it means that we have visited this node, but not all of its neighbors. So but not all of its neighbors. And whereas if we associate a node with a black color, it means that we finish visiting this node as well as its neighbors. So there is no need for us to visit this node again. So this is the meaning of this of the colors. And then next, for the south node, we're going to associate it with a gray color. And then so we're going to, what we're going to do is that so we're going to associate the south node with a with a parent that is neo, and then we create a queue. Okay, so here this means empty side. It means that we initially create a queue that is empty, so with nothing in it. So I'm not sure if you still remember queue. We learned this in lecture 4. So we say that queue is a data structure that supports efficient insertion and deletion. So so it implements the first in first out policy, whereas stack implements the last in first out policy. Still remember that? And to do insertion, we need to call the inqueue function of the queue, whereas to do the deletion, we need to so the deletion function has a special name called dequeue. Okay, so here what we do is that we insert the source node to the queue, and while the queue is not empty, meaning that the queue includes at least, so queue is not empty. Okay, well, the queue is not empty. So what we do is that first we dequeue, we delete a node from this queue, and we store the deleted node with in the variable u. And then for each node, v that is here g.adju. Okay, so here I think I need to explain two things. So first, what is g.adju? So we can say in the other way, the neighbors of u. Neighbors of u, okay, the neighbors of u. So, and we store its neighbors in a set. Okay, so v in, so this operator means in, and I think you should learn it from the discrete math course. Okay, so in means it's pretty much like an iteration. Okay, for every node that is inside this set. So if you don't understand what is a set, so for now you can take it as an array. Okay, for each value that is inside the array. Okay, and so then what we do is that for each node that is adjacent to you, or for each of your neighbor, so if its color is white, then we associate it with a gray color. and we set the distance of its neighbor as the distance of u plus 1, and then we set the parent of its neighbor as u, and then we enqueue we insert this its neighbor to the queue, and finally after we do this for all of its neighbors, we associate this node with a black color. Okay, so this is the pseudocode. And next, my main task today is to explain why and how this algorithm work. So I'm going to use an example to go over it. So let's say we have BFS, G, and S. So for each node U that is inside G dot V minus S, so it's like for each node that is inside this graph, but excluding the source node, we associate it with a white color, and then we associate it with a distance that is infinity, and we associate it with a parent neo. And so after this for loop, what we do is that we, for the source node, we give it a gray color, and then we so we set its distance as 0, we set its parent as neo. Okay, so this is the first part of the code and pseudocode, and I'm going to use one example on the right hand side to explain it. Okay, so here we have a graph with 8 nodes. We have so in a textbook they call them like RSTUV, etc., etc. But now let me just give it a different name. Like we have node A, B, C, D, and E, F, G, H. Okay, so the structure of the graph is like this. Okay, so suppose here in this example we say we have such a graph, and we pass this graph G into the BFS algorithm. We set S as B. So we basically take this node. I'm just going to use a red color. We say this is our starting node. Okay, this is our source. We want to know the minimum distance from this node to every other node inside the graph. So first, for each U that is so let's look at the first line. For each U that is inside the graph, but excluding the source node S. So let me explain this one in a relatively slow speed. G dot V meaning the set of nodes in the graph. So for the set of nodes, we have A, B, C, D, E, F, G, H. Okay, and here we have, if we have G dot V minus S, it's like so here we have S as B. So it's like we want to exclude B from this set, or from this, you can take it from this array. So it's like we exclude this node, and what we got is that for each U that is inside this set, okay, with A, C, D, E, F, G, H. So in the first round of the for loop, we have U as A. So what we are going to do is that, so this is U. I'm going to put a U right over here. So this is U. We're going to give it according to the pseudocode right over here, we're going to give it a white color and give it an infinity distance and a neo parent. So I'm going to write everything down. So it has a white color. I'm using W for white, and then infinity distance, neo parent. And in the next round, we have U as, so because we need to skip S, which is the source node. So So then we put U right over here. So at C, so we do the same thing. Okay, we associate it with a white color and infinity distance nil. And in the next one, we are going to put U right over here. We're just going to assign D as U. So for this node, we have, in this node again, we have W white infinity and nil. Similar for all the other nodes. So I'm just going to write them down very quickly to save some time. W infinity and nil. Okay, and so then we just finish this for loop. We're done with here. We just finish right over here, and then we're going to start s dot color as gray. So remember, this is s, so this is s, so this is our source node. So we are going to associate it with a gray color, and with a distance that is 0 and its parent is nil. Okay, so let's look at first why we associate it with a gray color. If we go back, you probably know, okay, gray color means if a node has a gray color, it means that this node has been discovered, but not all of its neighbors. Okay, so here we give the gray color by acting like this. Okay, in the morning, you just pick up your mails at here at Frankfurt, and you are already at Frankfurt. So this node or this city has been visited, but not its neighbor cities. So that's the reason why we should give it a gray color. And also we set we give it a distance as 0. So we set s dot d as 0. The reason is that we have first node v dot d denotes the minimal distance from the south to the south. Okay, so let me ask you one question. What is the minimal distance from your home to your home? So you are going to say, okay, are you crazy, right? So it's of course 0. Again here, okay? Same here. If you are in the morning, you are at Frankfurt, and so this is your starting point. And if I ask you, okay, what is the minimal distance from Frankfurt to Frankfurt? You will definitely say 0, right? That's the reason why we associate the south node with a 0 distance, because of course it's 0. And before reaching the south node, by using the shortest path, there is no node that you're going to visit before it. That's why we assign neo as its parent. Okay, so we just finished this first half of the algorithm. We just finished up to here. Okay, and then we're going to go over the second part of the algorithm, which is a little bit more complicated. First, we create an empty queue. Let me remove this part also. So we have an empty queue. Okay, let me just remove, write down everything at the top, so it's easier for you. So we don't have to scroll the screen. So the second part starts with this queue. We create an empty queue, and then we enqueue q and s, and then while queue is not empty, so we dequeue. We have dequeue, and for each node v that is adjacent to u, okay, and so if v dot color is white, we set v dot color as gray, and we set v dot distance as u dot distance plus 1, and we set the parent of v as u, and finally we enqueue it. Okay, and then after we finish this for loop, we are going to say associate the node u with a black color. Okay, so this is what we do right over here. So first, let's start from this line. We are going to create an empty queue and enqueue. So first we have an empty queue right over here that is empty, and then Now, so after we do enqueue, we have the first node, which is B, right over here, right? So which is B, which is our source node. I'm going to use red color to denote that this is a source, our source. And then, so we go to this line, we go to the line right over here. While the queue is not empty, of course, this queue is not empty because it includes one node, okay? So we dequeue, so this node is going to be removed. And then we got U equal to B. So we have U as B. So I'm going to put U right over here because U is this node. This node is just U. And for each V, so for each V, that is the neighbor of U. So the neighbor of U includes A A and F, right? So we have A and F. So, and then first let's have V as A. So we have V as A. So I'm going to have, so V as A. I put V over here. So V is here. This is the node V. Okay. If the color of V is white, yes, its color is white. So it passes the if statement, and then we're going to be able to execute the four statements inside the if condition. So V dot color equal to gray, so we associate it with a gray color. And then we're going to set the distance of V as U dot D plus 1. We have U dot D as 0, so U dot D plus 1 is 1, so we set its distance as 1. And we set V dot pi as U. U is S, so we say its parent is just S. Okay, and then we enqueue it. So now sorry, this is not V, this is A. Actually, this is A. So we add this node into the queue, and then so in the next iteration, we just pass this iteration. So in the next iteration, we have V equal to F. So we have V right over here, and we're going to do the same thing. Okay, so we check if its color is white or not. Yes, it's white, so we're going to give it a gray color. And we're going to set its distance as U dot D plus 1. Here we have U dot D as 0, so its distance is going to be 1. And then its parent is going to be U, which is S. So, okay. And then we just finish this iteration, so that will finish the for loop. And then finally, we will be able to execute the last line, which is U dot color equal to black. So we just set its color to black. Okay, and this is what we do in this iteration of the while loop. So then we just go back to the while loop again. Sorry, I forgot to do the enqueue thing. Okay, for the node F. So F is also in the queue, and then then we go back to the while loop. So we check if the queue is empty or not. So obviously it's not empty. So I'm just going to remove the U and V sign right over here and also over here. Okay, so then we're going to dequeue. Okay, so if the queue is not empty, we're going to dequeue. So A is removed, and then we have U as A. So U is here. Okay, and let's check what are the neighbors of A. So the neighbors of A include two nodes, which are B and E. So first we have V equal to B. So I'm going to put V right over here, and we check if the color of V is white or not. No, it's black. This node has a black color, so the if condition fails. So we just skip the following statements, and then we start another iteration with V equal to E. So I'm going to put V right over here. Okay, this is V. And we check if its color is white or not. Yes, its color is white, so we're going to give it a gray color, and then we're going to set its distance as U dot D plus 1. Here we have U dot D as 1, so 1 plus 1 is 2. So we set its distance as 2, and then we set its parent as as u, which is a, so its parent is a. So then and then we also do enqueue. Okay, we just enqueue e into the queue. Okay, so then we finish this for loop. So then we just go to, we're going to set the color of the node u as black. So this node turns black, and then we finish this iteration in the while loop. So again, we are going to check if the queue is empty or not. So it's not, so we're going to dequeue. So we remove this node. So here we got u as f. So we're going to put u right over here. And then for each neighbor of u of f, basically for each neighbor of f. So let's check what are the neighbors of f. For f, its neighbors include b and C and G. Okay, so according to our previous experience, what we know is that, okay, if a node, so for all of its neighbor, we are only going to do some operation over its neighbor that has a white color. So here we can say for its three neighbors, obviously B does not have a black color, so it's not going to be processed. So that's why we so we can just skip that for now, and if we can safely skip it, and then we start this for loop with v equal to c. So I'm going to put v right over here. So because its color is white, so it passes the if statement, and then we're going to associate it with a gray color, and then we're going to set its distance as u dot d plus 1. So u dot d is 1, so plus 1 is 2, and then we're going to assign u, which is f, as its parent. So its parent is f. So and then we do enqueue. Okay, so c goes to the queue, and then we finish this iteration. Next, we're going to start another iteration with v equal to g. So I'm going to put the sign of v right at g, which is here. Okay, so its color is white. So what we do is that we set its color to gray, and then we set its distance as u dot d plus 1 is 2, and then we set its parent as u, which is f. Okay, so we also enqueue it. So g also goes to the end of the queue, and so we finish this for loop, so that we're going to set the color of g as black. The color of u as black, which is f. So its color is black, and then so we go back to the while loop. The queue is not empty, and we dequeue one. So we remove e. So we have u as e. So let me remove this v, and so we have u as e. So u is here, and the neighbors of u includes includes just a. So but a has a black color, so we're not going to do anything for that node, and so we just jump to the last line, set is the color of u as black. Okay, and so we next we are going to go over the while loop, so it's not empty, and then we're going to dequeue. So we have u as c, so c has been dequeued, and we put the u sign right over here, and then so the neighbors of u of c includes what? Includes f, d, f, and g. So among these neighbors, only D has a white color, so only D is going to be processed. So so we're going to set the color of D as so we put the V sign over here, and we are going to set its color as gray, and we are going to set its distance as u dot d plus 1. So 2 plus 1 is 3, and we are going to set its parent as c. Okay, its parent is c, and then we're going to enqueue it. So it goes to the end of the queue, And then after finishing that, we're going to set the color of U as black. So this node turns black. And then we go back to the while loop. So the queue is not empty, we're going to dequeue. So we have this node come out of the queue, which is G. So I'm going to put the U sign right below G. Okay, this is G, and this is U, and the neighbors of G includes, so here we find that it includes C, D, F, and W. Sorry, C, D, F, and H. So among them, only W has a white color. So only W will be processed. Only H will be processed, and so we can put the V sign right over here, and then we're going to set its color as gray, and we're going to set its color as gray. We're going to set the distance as 2 plus 1, 3, and we are going to set its parent as G. Okay, as U, which is G. So and then we're going to enqueue it. So it goes to the end of the queue. So then after we finish this for loop, we're going to set the color of U to black. So this node turns black. And then we go back to the while loop. So we do dequeue. So D is going to be eliminated from the queue, and so its neighbors include C, G, and H. None of them has a white color, so we're not going to do anything for its neighbors. We are going to simply set its color as black. So this is black, and then so we do dequeue. Okay, so we go back to the while loop. We do another dequeue. So H is removed. So H is removed. So we put H right. So this is our U. Okay, this is our U. So its neighbors include D and G, but none of them has a white color, so we're not going to do anything for its neighbor. And then we simply set its color to black. And then this concludes the algorithm. Okay, so then we go back to the while loop. We find that the queue is empty, so so the while loop is terminated, and we don't do anything after that. Okay, and this terminates the execution of the algorithm. So let's look at what kind of output do we get. Okay, I'm just going to use the purple color to denote it. So previously we said that we expect the algorithm to return the minimum distance from every other node to the south node. Okay, so here let's just, for example, for this node H, we want to know what is the minimum distance from it to the south. Okay, so the answer is right over here, is 3. And then some of you may wonder, okay, so how do we by following which route can we get this minimum distance? And so here from H, we know that its parent is G, so it means that we need to follow this route. Okay, so for its parent G, its parent is F. Okay, for F, its parent is S. For S, it's not S. This should not be S, should be B. Okay, it's B. So for B, and also this should be B. Okay, so for node B, its parent is neo. So yes, this is the shortest route that gives us the distance 3. Okay, so you can check this by yourself for the other nodes, and this is the end of the algorithm as what I showed in this picture. But I think my illustration by using the example over here is more clear. Okay, so next I want to briefly talk about the complexity of the algorithm. It is V plus E, the number of nodes plus the number of edges, because each node is going to be visited exactly once. Okay, so this is the breadth first search algorithm. And actually, there are two search algorithms, so the other one is named the depth first search, and this one is going to be more complicated, way more complicated than breadth first search. So I'm just going to briefly discuss the difference between them. Okay, so let me first explain the idea behind breadth first search. BFS. So BFS is like this. If this is your home and then you want to visit other places in the country, so with breadth first search, the logic for to do is that first you are going to visit the neighbors of your home. Like, so for example, if you live in Montclair, you're going to visit Natalie or Clifton, some areas. And after you visit all the places within, let's say, 50 miles radius, you are going to increase your radius. So now you go to Philadelphia, you go to you go to visit every place within 100 miles of your place, and then you gradually, so each time you pick a radius and you finish visiting all the places within the same radius, and then you increase your radius. Okay, so this is the idea of breadth first search. And for depth first search, if this is your home, the logic is that, okay, so in the beginning you pick a direction. Say, for example, if you want to go north, then you are going to visit every place to your north. Okay, so and then you come back to your home, and then you pick another direction. For example, say now you want to go west, so you visit every place on your west, and then come back home, and then visit, for example, south, and then come back. So like depth first search is like after you pick one direction, you go to the very deep of that direction and then come back. So this is the difference between breadth first search and depth first search. So for depth first search, because it's really complicated, so I don't expect you to have a very good understanding of it. And actually, none of your job interviews would ask you to implement depth first search, because it's not going to be feasible within 45 minutes. But for depth first search, the only thing that I expect you to know are as following. Okay, for breadth first search, as you may know that we associate each node with a distance, which is the minimum distance to the south, and a color and a parent. Okay, so here for depth first search, we associate each node with a D, a F, and a parent pi and a color. So the parent and the color of breadth first search and depth first search have the same meaning. So they just denote the same thing, but the D now D does not mean minimum distance. It means something else. It means this, and also F means something else. Okay, I'm just going to tell you. D means what? D means the time when you go to visit the place for the first time. So for example, okay, on day 1 you visit this place, on day 2 you visit this place. So for this node, its D is just 2, and then you go to the very north, and then you come back home. Okay, F denotes the second time that you pass by this city. Okay, it means and after you pass by the city for the second time, you are not going to visit it anymore, because next time you are going to pick a different direction. So that's why I say that D means the discovery time. It's like when do you just discover this node for the first time, and F means the finishing time. When are going to, or farewell time. When are going to say farewell to that place. So this is what we mean. And also the time complexity of a DFS is also V plus E, so which is the same as BFS. So next, I'm just going to briefly talk about your homework 8. So in your homework 8, you're asked to implement the breadth first search algorithm, and this is mandatory. And also, if you want to get if you want to get 100 extra point, you can optionally do the DFS search algorithm. If you implement it correctly, you will get 100 point extra credit. So if you don't do good in your previous homeworks, this is an opportunity to make your grade up. Okay, so yes, that's everything that I want to talk about today, and have a good week.